So actually we'll start by review of linear systems. Linear systems theory. How many of you took 270A or a course on linear systems? So linear system theory, so this is x dot equals a of t x plus b of t times u, x lives in Rn, y is the output, right? And here we're saying the system may be even time varying, so A, B, C, and D may depend on time. We have initial condition x is 0. It's just x0. We know a lot linear systems, so this is like a summary if you didn't take the course. It's a summary if you took it also, it might be a good summary for you. So we know a lot. We know the solution, an analytical solution for the system. In terms of the variation of constants formula and the fundamental matrix. So this is your fundamental matrix 5t. Please stop me anytime if you have any question. So this is x0. The fundamental matrix is the solution of your system due to n independent initial conditions. Each one is a column. Stack them together, you get this matrix, even if it's a time varying system.
Professor, what is y here?
What is?
Y.
Y is the output. So the set of variables that you're typically interested in, the set of variables that you're typically able to measure. So here, integration 0 to t, phi t minus tau times your thing. This is the variation of constants formula. B of tau, u of tau, d tau. So you know the solution. For LTI, linear time invariant, this phi is just e to the at, right? For general time varying system, so if I have a of t time varying, we don't have an analytical solution for it. You can go and try to approximate things. This is the identity plus at plus a squared t squared over 2, yada yada. Which is, if you want to compute it, you can do Laplace inverse of Si minus A, all inverse. Actually, in MATLAB, you can just type xm, right? Matrix exponential of A times T. So it gives you this directly in MATLAB. And because we have a solution, we can talk about stability, and we have a sharp condition, at least for LTI. It's if and only if, right? The eigenvalues of your A matrix, they have strictly negative real part. If you have a question, let me stop. We can discuss anything, and I will give you some time to write. We also have the case for linear time periodic for the Fouquet theorem, but yeah, we will talk about it later. Other than that, other than linear time invariant or linear time periodic, we don't have a theorem. So, what else? We can talk about controllability, right? And again, we have actually sharp condition. We have if and only if condition. The controllability Gramian W of t is 0 to t. This is your phi, negative tau, b of tau. This is for even time varying systems. Phi, negative tau, transpose, d tau. And this guy is invertible for all t. Then the system is controllable. And for linear time invariant, this condition is exactly equivalent to the famous condition, the rank of B, AB, up to an minus 1B is full rank A, right? Controllability, so this is one property that we have a sharp condition for controllability. Another property for controllability of linear systems that it's constructive. We talked about this before. I guess in our previous lecture where I mentioned the W and this law, control law, I think it was not the correct format. There was maybe one couple of signs missing or whatever, something. So I think this is the correct format because I derived it, so I remember it now. So this is negative B transpose of T, and it can be for time varying system, that's fine. Phi, your fundamental matrix solution, negative tau transpose. You just said that W is invertible, so please invert it. And this is at the final time. Here we have x naught minus phi, negative tau, negative t final. That tau here, this is t. We need u of t, so this is t, this is t. This is t final, x phi. You can find the formula in Brockett's book on finite dimensional linear systems. When this guy steers your system, let's say 1, from x naught, right, to x final in t final, and actually minimizes the control energy. Okay? So controllability is sharp, controllability is constructive. Controllability is feedback invariant. And actually, Professor Kia likes to have questions on the prelim about this feedback invariance if you're going to the prelim. So, by feedback invariance, I mean if you introduce U to be like whatever, K X plus V, right? Some feedback and your transformation. So your new dynamics, if it's LTI, it's A plus BK, right? In the X plus BV. So your original A and B matrix, this pair was defining your previous system, so this is controllable if and only if the new pair, which is A plus BK, this is your new A matrix, your new B matrix is the same, is controllable, right? And the same for invertible transformations. If you define, say, x equals tz, so your new system is z dot is t inverse at z plus t inverse b, right? The pair A and B is controllable if and only if t inverse t and t inverse b is controllable for any invertible transformation t. So it's feedback invariant, which should be the case, right? The controllability is a property of your system. So I have my system. I have a bunch of actuators. This is my system physically. So if it's controllable, it's controllable. It doesn't depend on your way of representation. You're represented by this states or these other states. It's up to you. The system is controllable. So this is an intrinsic property. So if your check reflects this intrinsic property, it's a good thing. So the linear check reflects this property. That's feedback invariant, transformation invariant. Controllability, these are all properties of controllability. Linear systems. We're doing linear systems review here for those who came late. So controllability implies stabilizability, which kind of makes sense, right? I mean, if you're able to control the system, you should be able to stabilize it using static feedback, like U equals Kx. Okay? So this is not the case in nonlinear systems. We will talk about it 2 lectures from today. If it's controllable, it's not necessarily stabilizable using static feedback. So these are all properties of controllability. And this guy in particular invokes control design or stabilizability. So if you want to do stabilization, it's straightforward to do state feedback, right? And actually this control law for LTI does what? Does pole placement, right? Eigenvalue assignment. You place your poles to have the closed loop characteristic equation looks like some alpha of S equals 0. So this is desired characteristic equation. So it's a given. Okay? One way I'm reminding you, doing review here, I mean you can compute it several ways, but for single input, for example, you can compute this K by the Ackermann's formula, right? So it's very constructive. The linear system theory is very constructive. It's U01's controllability matrix inverse times alpha of A. This is the desired characteristic equation, right? So it's just polynomial of S, replaces each S by A. So the resultant alpha of A here is a matrix. This is your controllability matrix, B, A, B, A squared B, and yada yada. Multiply by a row, you get the gain row here. For linear systems, you also have the problem already solved for optimal control. So we have, whole theory very well developed, very mature. Sometimes we give things like LQR. So we want to regulate our systems, linear quadratic regulator. We already steered my system to the point I want. And now I want to just regulate it. I want to just maintain this state without loss of generality, assume that it's the origin, so I don't want my x's to deviate from the origin anymore. So I want to minimize, I want to regulate around the origin and minimize something like any quadratic cost, maybe x transpose qx, and this makes sense to minimize it because, like I said, I want my x's to be as close to the origin as possible, so I want to minimize the norm of x. This is the weighted norm of x. Plus, I want to do that with minimum control, so this is u transpose ru. Again, I'm minimizing the norm of u, and this is the weighted norm. So q and r are given. These are your weighting matrices. R should be positive definite in order to invert it. And it's solvable, right? Again, u is negative kx. With K is given by R inverse B transpose P, and P satisfies algebraic cat equation. So A transpose P plus PA plus P B R inverse B transpose P plus Q is 0. The solution of this equation gives you P matrix. Plug it here, get your gains, and you're done.
Professor?
Yes.
I have a question. So why did we derive a new condition for the optimal control and not using the steering one?
That's a good question. This is a very good question actually. I mean, because it will pose the following point. We are here in this course and the community are obsessed with steering, motion planning, right? This will just touch the point x final.
Okay.
So, okay, let's see. You have an airplane and I want to attain a higher altitude and higher velocity. Can you do it without increasing your thrust, for example? It seems not, because from where I will get the energy. But the point is that we're not after balance. You will not go there and stay there with higher altitude and higher velocity. You will just touch it. So you can do any fun things with your control surfaces and the engine manipulated. Just go and touch it instantaneously, and then you'll do something else. So this is motion planning. I will go and just touch it in the state space. To maintain it it means that it has to be an equilibrium point. Equilibrium necessitates balance, and balance necessitates creation of forces. We are not here about after creation of forces at all. Creation of forces is so hard. This is why in the symmetric product we were a bit happy that we can create forces. Okay? So this guy doesn't even create an equilibrium, but it maintains an equilibrium. The objective here is for actually infinite horizon. So we're interested in the infinite time. We're gonna maintain this. So we're gonna reject disturbances, irrespective of your disturbances. This is control about a set point. Okay? So you should, if you want to do the full problem, steer up to there,
And then,
but then you have to create an equilibrium. You're going to change parameters in your system or some control value, thrust, elevator, whatever, to make it actually an equilibrium, so you can stay there, okay? And then you can stabilize it, stabilize and maintain, okay? So we have lots of things. I will just change here, finish here. We have duality, right? Between controllability and observability. So you can, whatever I said for controllability, LQR, controllability check, whatever, you can apply it exactly the same for observability by just transposing your A and C matrices, right? And consider them as new A and B and do the controllability things. In particular, the LQR, the analog here, anybody knows what's the analog of LQR? What is the analog of the linear quadratic regulator in the observability case? Kalman filter, right? So Kalman can be actually thought of as an LQR problem. This is Kalman filter. And
But some properties don't carry, like feedback invariance, for example, doesn't carry those.
yeah, feedback invariance doesn't carry because you feedback doesn't change zeros. Yeah. So and you guys know that LQR plus Kalman is what? What's that? LQG, linear quadratic Gaussian. So you design both simultaneously, a controller and an observer, right? And it has been thought for a long time, you know, designing a controller and an observer independently, because we have a theorem for decomposition by Kalman. If you design this independently, this guy independently, they work perfectly fine, and indeed they do, except that they are not robust at all. So this was known until that very famous paper by John Doyle came and said, hey, I can change this little bit of your A matrix and everything will blow up. So this, initiated the robust control, which again, it's very well developed for linear systems. I'll stop here. So this is like a summary for the linear systems theory, that the very well known tools. Any question about that? So we know a lot about linear systems, right? We know a lot. It's indeed very well